So now that we've covered sets, we can move on to discussing functions. So I'll discuss the general definition of a function, the real valued functions that we are interested in, and what we mean by the inverse of a function. Okay, so this definition is due to Dirichlet. If A and B are sets, then a function f from A to B is a subset of the Cartesian product A cross B, such that no two ordered pairs f have the same first element and a different second element. Okay, so basically what that's saying is that f maps an element of A to an element of B and to only one element of B. Okay, so for example, A is the set that consists of the elements 1, 2, 3. B is the set which consists of the nabla symbol and triangle. So f is equal, and then we define some subset of A cross B. Let's say it has elements 1 nabla, 2 nabla, and 3 nabla. So this is a function from A to B. And similarly, if I try something else, I try G is equal to 1 nabla and 1 triangle. Okay, this is a subset of the Cartesian product A cross B, but it's not a function from A to B. And the reason is that G is associating 1 with an element of B, and it's also associating 1 with another element of B, right? Each element of A can only be associated with one element of B. Okay, now the notation that we are used to is that if xy is an element of a function f, then we would write y equals f of x. Okay. Now some notation about functions and definitions. Supposing we have a function from A to B, then we call A the domain of f. If we have a function from A to B, we will call B the codomain of f. And the range of f is the set of all second elements of the ordered pairs of a function f from f maps A to B. So those are the actual values. For our purposes, these will be the actual values that f takes. Right? It may not map every element of A to every possible element of B. So the range will be a subset of the codomain. Okay, so here's an example. F is mapping reals to reals, and it's defined by f of x equals x squared. So the domain is the real numbers, the codomain is the real numbers, and the range is all the real numbers from 0 to infinity. So all of the non-negative reals, that's the range, which is a subset of the codomain. Okay. Some more vocabulary about sets. Injective and one-to-one mean the same thing. If f is a function such that for p and q in its domain, f of p equals f of q implies p is equal to q, then f is said to be injective or one-to-one. Okay, so here's an example. A is the set which consists of the elements 1, 2, 3. B is the set which consists of the elements nabla, triangle, and banana. Now f is 1 nabla, 2 nabla, 3 nabla, which is a subset of A cross B. So f is a function from A to B, but it's not one-to-one because it's mapping three different elements of the domain to only one element of the codomain. In order for it to be one-to-one, each element of the domain would have to be mapped to a different element of the codomain. Okay, so here's an example. F maps the open interval 0, 1 to the reals. F of x equals x squared, right? Is this injective? That is it one-to-one? Well, yes. If f of x is equal to f of y, that is, if x squared is equal to y squared, then we can conclude that x is equal to y. Okay. Let's take another one. G maps the open interval from -1 to 1 to the reals. G of x equals x squared. Is this one-to-one? Well, it isn't. For example, g of 1/2 is 1/4, and g of -1/2 is 1/4. So you've got two elements can be mapped, two elements of the domain can be mapped to one element of the codomain, and so it's not one-to-one. Surjective and onto mean the same thing. If f is a function which maps a to b, it is said to be onto b if its range is all of b. Another way of saying this is that for every b in b, there is an a in a, such that f of a is equal to b. Okay, so here's an example. A is equal to 1, 2, 3. B is equal to nabla triangle. F is 1 nabla, 2 nabla, 1 nabla, 2 triangle, 3 triangle, sorry, is a subset of A cross B. Each element of the domain is mapped to some element of the codomain, different, right? This is onto because the range, these are the second elements of F, is the same as the codomain, right? The range of this function is nabla triangle, and the codomain of this function is nabla triangle. So this function is onto. Okay. Let's try another one. F maps reals to reals is defined by f of x for all real numbers x. Is this onto R? Well, no, it isn't, because there's no x such that f of x is equal to -1, for example. So the negative numbers are not in the range of this function, but the codomain, the reals, does have negative numbers. So the range of the function is not the codomain of the function. Okay. We move on to real valued functions. We're mainly concerned with functions that will map some subset of the reals to a subset of the reals. Okay. Now, suppose you have two functions. F maps some subset of the reals to a subset of the reals. G also maps with the same domain. So what do we mean by F? So we have a function F, we have a function G. We create a new function, F plus G. Well, what do we mean by F plus G? Well, F plus G is the function such that if it acts on A, it gives us F of A plus G of A for all A in the domain of F and G. Okay, what about the difference? Well, if F and G have the same domain, which is a subset of the reals, and they're mapping to the reals, some subset of the reals, then we have a function F, we have a function G, we define a new function, F minus G. Now, that new function f minus g is the one such that when f minus g acts on a, it gives us f of a minus g of a. Okay. Product of real valued functions, well, if f and g have the same domain, then by f times g, we mean that function such that f times g acting on a gives us f of a times g of a for all a in the domain of f and g. Scalar functions, this is a special case of the previous one. If f is a function from a to b and c is some real number, we define a new function called c times f. And by c times f, we mean the function such that c times f acting on a gives us c times f of a. Quotient of functions, you need to be a little bit careful, always with quotients. Let's suppose that f and g have the same domain. Then by the quotient f divided by g, what we mean is that that new function acting on a gives me f of a over g of a for all a in the domain of f and g, except if g of a is equal to 0. Okay, and now we define the composition of functions. Supposing that f maps a to b and g maps b to c, g composed with f maps a to c, and it's defined like this. The composition of g with f acting on a gives me g of f of a. Okay. Inverses of functions. Now, supposing f maps a to b, g is mapping in the other direction, from b to a. Supposing that the composition, g composed with f, acting on a, gives me a for all a and a. And also, f composed with g, acting on b, will give me b for all b and b. Then we call g the inverse of f, and we call f the inverse of g, and we say that f is invertible. This requires an inverse of a function exists if and only if f is 1 to 1 and onto b. Okay, so for example, f maps reals to reals is defined by f of x is equal to x squared. This is not invertible. Now, why isn't it invertible? Well, one reason is that, as we saw before, that map is not onto the reals. Okay, let's consider f sends negative numbers to the negative numbers, defined by f of x equals x cubed. So why is f invertible? I'll let you think about that. And exactly, you already know what the name of its inverse is. Okay, so that ends our discussion about functions.